That's the same page 7. That's the second example of that page. Again, I say similar because I just changed this a little bit. So this example, when you look at it, it requires some irregular intervention because it's a polynomial of degree 9. In general, we don't know how to do that. But in this particular case, if you look closely at the polynomial, do you have any suggestions? We can group them in a special way. We can group this first one with the third one and the second one with the last one. If I group that, that's my grouping. These two together and these two together, and that actually gives us the ideas what to do next. We have to factor out common multiples here and common multiples here. If I factor that out, it will be x to the 4, x5 plus 1, 16, x5 plus 1. And now we can factor even further. Now we can factor the whole bracket. And that's the whole bracket give us something like this. It's not a complete factorization. Remember, when we go after factorization, we go after the polynomial of the lowest possible degree. And for the polynomial with the real coefficients, at least we should bring it down to squares. Or in complex terms, even to the linear polynomials. But this time, these two can be factorized with the method we did the first example today, with the knowing the roots of a complex number. So it's sort of a combination of the second solution and the first one. First, we did some manipulations with the polynomial, reducing to something simpler. And then now, for these two simpler brackets, we can do roots of a complex number. So if I look at the first bracket, we look at the equation like so. I already made this -1 in exponential form. For the second bracket, we look at something like this. Again, -16 converted to exponential form. Now, again, without giving you much of the details, we did this a few times last time. So we have solution here. We have here 5 solutions. If I find this, here we have 5 solutions for the first equation. We have 4 solutions for the second equation. The way we find solutions to the way we find roots of a complex number. They are all pictured here. Red vectors, that's the zk. Blue vectors, that's the w. So for instance, w0, this is z1. Now it's time has come to factorize things. Of course, we can factorize over complex numbers, like so. I just put all of these linear factors in, and I use the dots to save time in writing. And you can use the same dots when you save this, when you write this, because we already identified what z0, what z4 is. That's the half of the factorization. The other half involves w numbers, 4 of the w numbers, and that's the factorization over C, over complex numbers. More interesting is the factorization over real numbers. More interesting is, of course, factorization over reals, and here again we observe this phenomenon where solutions comes in complex conjugate pairs. Look at this one, complex conjugate with this one, complex conjugate with this. We also observe this phenomenon that the equation of the odd degree, say for instance this 5 or this 9, has a 1 root, which is a pure real number root, no complex conjugate pair. Right, so let's just combine this. Here's my combination. Look at this. First, let me identify real parts. The W0 number, real part of the W0 number, look at this, is number 2, and that's a 45 degrees angle, so the real part here is just root 2. This number, it's a Z0 number. The real part here is a bit trickier. What's the real part of this number? You have to multiply the length of this vector, which is 1, by the angle here. What's the angle here? Pi on 5. So I just keep it this way, cos pi on 5. For this number, for instance, if you do a little bit of arithmetic, you will find the argument cos 3 pi on 5. After we identified all of these components, we can now build my factorization over real numbers. Look at this. That's my factorization. First comes my linear factor, the existence of which we predicted before. Here it is. That's the bracket which corresponds to this root. Next goes square, double of the real part, double of this real part. We now factorize for the red solutions. And then square of the length, which is 1. length of this vector. And that's the bracket which corresponds to these two complex conjugate solutions, this solution and this solution. For these two solutions, Z1 and the one which is complex conjugate, for Z1 we have similar trick. Look at this. We got we got 2 of the real parts, and the real part here costs 3 pi and 5 now, and the square of the length, which is 1. These 3 brackets, they correspond to this complex part in this factorization. Now for the W part, we will have 2. If I find them, it's here. For the W part, we have x squared take 2 of the real parts, 2 of the root 2, this real part, plus the length of my vector. The length of my vector is 2. Here it is. That's why it goes, oh, it should be square in fact, right? It's a typo. I just realized this. I'll fix this in a second. And the second bracket will be x squared plus 2x root 2. That's this real part. For this complex conjugate pair. And that will be another, well, in fact, 4, right? Let's just fix this. 4. Do you agree this is 4? Yes, thank you very much. That's 4. And that's the factorization over real numbers. That's where the question stops, in fact. You don't have to go any further. But with our knowledge, with what we discovered with what we discovered with you before, we can actually take this question further because you, in fact, you know what the sine of pi and 5, you know this value, and that's why you can actually find the actual values for cos here and for cos here. But this one you will do independently.